Okay, so I'm gonna finish from the two slides that we had from the previous lecture that we didn't cover. So we're talking about joint distributions mostly, and I'm going to talk about the particular mechanism uh, m- by which two random variables become um, dependent. And this is very common and it's very useful to kind of have in mind. Talk a little bit about multivariate normal, and then most of this lecture is going to be talking about conditional expectation and the results related to conditional expectation and conditional variance. Okay, so the example that I wanted to like spend some time on is this shared hidden cause or something like that. So if you have, let's say, independent variables z and then epsilon x and epsilon y, assume that z is a normal random variable mean 0 and tau squared, and the epsilons are um, supposed to be noise. So 0 mean variance sigma squared. And because they're independent, we didn't really talk too much about the joint distribution of three random variables, but they're going to be jointly, is something that we haven't seen much, but they're going to be jointly normal, or at least we know the joint distribution. Okay, so I can, for example, write the joint density, which will have three variables, and this would factorize. So let's say z, um, uh, let's say alpha and beta, for example. This would factorize into the components because of independence. And so we have a full distribution, okay? And we have a full joint distribution for these three random variables because of independence, and we know that the individual PDS are normal. Okay, and then any function of these random variables would then we can determine its distribution or any basically pair. So for example, suppose I set x equal to z plus the noise epsilon x, and then y is z plus noise epsilon y. Okay, um, then the pair xy will be a function of this triplet, and so it will have a complete description of the joint distribution. Whether we can write it or down or not, that's the second issue. But we'll have a joint distribution, and intuitively, what this is doing is these are easily observed, like or visualized as kind of diagrams that look like graphs with directed edges. So assume that this z is a random variable. This is kind of influencing x, and also epsilon x is influencing. So x is really a function of both epsilon x and z. So when you um, graphically represent it, x will have parents. So these are going to be the parents of x, which means x is constructed or is a function of z and epsilon x. Y is a function of z and epsilon y. And so they determine y together, and z and epsilon x determine x together. So these two pieces are independent of each other, but z is influencing both x and y. So they have a common component, which oftentimes happens if you think of this as a hidden cause. Okay, so this is like a hidden cause of these two. Uh, I mean, in this case, it's not hidden, but let's say if I just observe like x and y, I don't tell you anything about z, you just observe x and y, you would see that they're dependent because they both depend on x. Sorry, depend on z. And so this situation often happens. So you look at two random variables and you see um, that they're dependent. Oftentimes, maybe there is some hidden, unobserved common cause that kind of influences both, and you would get the situation. So the independence like arises from a mechanism or like a causal kind of model. So this, for example, Z could be the patient's latent true level of some um, um, I don't know, some characteristic like the blood pressure, and then you measure it twice, maybe today and maybe tomorrow, they're kind of like you observe fluctuations due to like, let's say, either noise or some other environmental factors, but the kind of the base like level of health of the patient potentially like affects both. So these two measurements of the same quantity from the same patient will be correlated highly because there is some sort of underlying biological factor that's common. And so mathematically, this is the easiest way is like basically x is just z plus epsilon x and y is z plus epsilon y. It could be more complicated function. Each one could be like a more complicated function of both. But then if this is this linear case, we could easily compute the covariance, for example. I can compute the covariance of x and y. Anyone knows how to compute the covariance of x and y? So there's like a easy way of doing it. So if I want to compute this, I get covariance of x plus epsilon x and then the z plus epsilon y, right? Anyone remembers how to do this? Sorry, this is z. Rather than trying to write down the expectations and try to calculate the expectations, you could use properties of the covariance. Anyone remembers the like a key property of the covariance operator? Anyone? So expectation is linear, covariance is anyone remembers? Covariance is bilinear. Okay, I can use bilinearity. Bilinear. So how do you use bilinearity? Anyone? I can distribute it as if these are like polynomials. You're just multiplying two expressions. That's what bilinearity means. So like this times this, which would be like z and z, plus this times this would be covariance of epsilon x and z, plus cov epsilon, or maybe z and epsilon y, all the four terms if you distribute it, plus cov epsilon x and epsilon y, right? Anyone sees this? Like, what is this? What does this evaluate to? What are each terms? Do I or am I on? No one wants to. So what is this value? Covariance is z and z. That would be variance of z. How about the other terms? Other term? This one? If I have two random variables that are independent, yeah, so they're all zero because the errors are not correlated, or I assume that they're independent. So all that the three are mutually independent. So mutually independent is stronger than uncorrelated as mutual. If you remember, if random variables are independent, they're uncorrelated automatically. The reverse is not true, but by assumption, z and epsilon x and z and epsilon y are zero, like these are uncorrelated, so this they're all evaluate to zero, and the variance of z is by definition tau squared. So you can see that they are correlated, and the correlation is exactly the variance of z. Okay, so if this is increased, then they're more. They're actually not the. It's not the correlation. It's covariance. So if you want to calculate the correlation coefficient, we need the variances of both, and you can compute the variance of x and y. Because the two components are independent, it's just going to be the variance of z plus variance of epsilon x, for example, and same for y, the same situation. You get tau squared divided by sigma squared, and then if you write down the definition of the correlation coefficient, I'll let you do it. Uh, you get that it's tau squared divided by tau squared plus sigma squared. So this is between 0 and 1. So the ratio of the variance of z and epsilons would determine the correlation. If this tau squared relative to epsilon is large, then this is close to 1. Otherwise, it's going to be like if tau squared, for example, is 0, they're going to be like independent. And you can see it's always positive in this case. They can't be negatively correlated. How could we have gotten like a negative correlation? Does anyone can see like a simple idea if I wanted to make x and y negatively correlated? What would I need to change? So this is always non-negative, you can see. But the correlation in general can be positive or negative. In this construction, they're always it's positive. They go together because they have the shared common factor z. So how can I make the correlation be negative? Anyone? There's an easy like solution. There are different ways, but here there's an easy solution. Correlation negative means when one goes up, the other goes down. Can you like think of it like a simple modification to this model that produces negative correlation? Anyone? Just guess. Here's a guess. Although think about it, maybe if you think about it, let me know in the chat. I'm not going to give it to you. Okay, everyone's coming up. Like take x to be z plus error. Yes, okay, that's the easy way. So if you do z, for example, negative z here, z here, and negative z there. So you just flip one of the. So they're still like highly correlated potentially, but they're negatively correlated. When you go calculate, for example, this covariance, there's going to be a negative sign here, and the negative sign comes out here, and you get negative tau squared. Okay, so the correlation coefficient would be negative of this. They're going to be always negatively correlated. So I'll let you think about it. So this is a very good example to try and like get an understanding. And you can simulate this from this model and look at the scatter plots. Play with the, for example, I can like multiply this by 2, what would happen to the correlation, so on. So this is a very simple example of a Bayesian network, a so-called Bayesian network, or DAG models. Bayesian network. It's a way of graphically representing the dependence of random variables, sometimes called like a DAG model, because these are directed acyclic graphs. Like if you have a causal interpretation, sometimes it's called uh, structural causal model. Okay, this has a little bit more um, uh, more assumptions behind it. Okay, so this is really assumed to be causal. So if I manipulate it, it also tells me if I, like, for example, set it equal to something, what would happen to x and y. So these are really definitions in that case. They're not equalities in the sense that one side is equal, but like one is determined exactly by the other, not vice versa. Anyways, so these are very interesting. Like in if you go to like a higher course, like maybe like graduate course, people study these models. They could be more complicated. So like this could be influenced by some other variable, and then this could also influence that, and then this might influence the children of some other node, and so on. So it get very interesting. Okay. Um, the important thing here is that given z, okay, so they are a priori, like, sorry, if I don't tell you this, like x and y are independent, if I condition on z in this case, like x, um, given z, x and y are going to be independent. Okay, that's kind of the basic idea. If I give you z, what it means is that I'm going to fix z basically. Once I fix z, uh, this is no longer random, let's say, then they're only randomness is here, so they're going to be independent. But if I don't fix z, so they're going to be, so this is called marginal. Marginally they're not, so marginally dependent. This is what we discussed. So like basically the correlation is non-zero, but they're like conditionally independent. Conditionally independent. Okay, so what it means is that if I look at the conditional distribution, like you look at the conditional um, density of xy given z, this would factorize into x. I believe we talked about this briefly, maybe. Has the same meaning as. So conditional independence is the same as independence, but that appears like the factorization appears in the conditional distribution. So the conditional density of xy given z, in this case, would factorize. This is always true in this model. But the marginal distribution does not. So if you look at the marginal distribution, this you can't write as fx x times fy of y. Okay, so when we say marginal here means in contrast to the conditional. So the if you marginalize out z basically, then you just look at the pair. This does not factorize. But if you look at the conditional density, it would factorize. So this corresponds to this statement 2 here, that they're not independent. This is not independent. And then this would be 1, statement 1. Okay, they're conditionally independent. Okay, so this is also interesting to note. So two random variables can be conditionally independent given some other values, but marginally dependent. And this is an example. Um, so given z, the measurements are independent. After z is hidden or like marginalized or we don't give you, they become dependent. So the distribution of z kind of um, um, yeah. So let's forget about this statement, the second statement. But the conditional versus marginal is important. Any questions? So it turns out that in this example, the pair xy will have a bivariate normal distribution. The general bivariate normal distribution allows for general correlation. Um, so bivariate normal is like if you look at the density of x and y in that case, um, if you plot it, these are the contours. The contours would look like this, um, which they're elliptical and they're tilted. If they were independent, they would be like circular. There's no special direction here because they're positively correlated, tilted in this direction. If they were negatively correlated, they would look like this. Okay. So these are the contours, the level sets, the sets on which the density is constant. And they peak here. So if you look at it, it's just the values are higher here and then goes down. So you can plot the density. I'm not giving the density of the multivariate normal. But you can drive it. We're not going to drive it in this course. there's an alternative definition of a bivariate normal. So you can say x and y is jointly normal or bivariate normal if and only if every linear combination is normal. Okay, so this is equivalent definition without giving you the density, and it generalizes to higher dimensions. Okay, for example, in this case, it's easy to see if I look at any linear combination of x and y, it would be a z plus epsilon x plus b z plus epsilon y. And so this would be a plus b times z plus a epsilon x plus b times epsilon y. And these pairs are kind of independent Gaussians, and you can drive the density of this. We didn't talk about the what is called change of variable formula, but using the moment generating functions, which the TA is going to talk about hopefully today, and we'll come back to it later. You can compute the moment generating function of this because of independence, it factorizes the moment generating function, and you can show that the moment generating function of this has a Gaussian form, and so it has to be Gaussian um, because it's like a linear combination of a bunch of independent Gaussians. Anyways, so this is a more general form, and from this you can drive the density. And this generalizes to multivariate case. So if you have multiple random variables x1 up to xn, they're going to be jointly normal um, if and only if any linear combination is normal for any set of coefficients. The i's are kind of deterministic, the AIs. Okay, and then in another C, we talk about this family. So the both bivariate and multivariate normal distributions are characterized by the mean and the covariance and variances. So if I give you the variances and the covariances of the two pieces and the means of x and y, that is enough to determine the full distribution. In general, you would need the covariance, like the mean vector and the covariance matrix. So you need basically the variances of all the pairs and all the pairwise covariances. Okay. In the bivariate case, for example, the covariance matrix would be the matrix that has the two variances on the diagonal and the covariance of the pairs on off diagonal. In general, the pairwise covariances would be like all the possible n choose two pairs, and the diagonal would be all the variances. So this covariance matrix would be n by n. This would be a mean vector n by 1. In the bivariate case, it would be just 2 by 2 and 2 by 1. Okay, and a central feature of the jointly normal family is that the variables are like independent if and only if they're uncorrelated. Okay, uncorrelatedness and independence are equivalent in the jointly normal family. In general, independence implies uncorrelatedness, but not vice versa. But in normal family, they're equivalent. So uncorrelated random variables that are jointly normal are going to be independent as well. So in this case, if it turns out that tau is 0, then it forces the two random variables to be independent in this case. And you can see if the tau is 0, basically, you'd have a random variable that has mean 0 and variance 0. So it has to be 0 almost surely. So this is not there essentially. And so they're kind of independent. Okay. This is a rather quick introduction to bivariate or multivariate normal distribution. The defining property is key, and this property that uncorrelatedness implies independence, and the reverse is always true, so they're equivalent in the normal family. That's one of the main uh, properties that we need, and the fact that the multivariate normal family is like, or bivariate is determined by the mean and the covariance matrix. So these are the interesting properties. You can write down the density if you want. We may look at the moment generating function later, but the form of the density is not necessarily useful unless you want to do calculations. Any questions, comments? So I would encourage you to go through this example in details and try to understand what we discussed. It's a very good example to understand dependence, independence, conditional independence, and this connects to the idea of Bayesian networks and DAG models and causal inference and a lot of other things. And you can do a very simple calculation here like this to convince yourself that if you have the z, they're going to be correlated. If you flip the sign of z, they would be negatively correlated. And if tau squared is 0, they're going to be independent. It all can follow. So if tau is 0, the variance is 0. If you recall, I mentioned earlier, very early on, that if the variance of a random variable is 0, that the random variable is constant. And because the mean is 0, that constant has to be 0. So this is a 0, just exactly 0 variable. And so, and it also like consistent with the fact that tau squared being 0 means correlation is 0. So correlation is 0 in this case implies z is 0, and then this goes away. Sounds good? Question? Fine. Okay, pause 1 minute here. Any questions about this slide? Questions about this slide? No questions? Oh, by the way, the slides are unboxed if you want to follow it. I forgot to mention. They're uploaded if you want to write on it. Okay, so that concludes the discussion of dependence for now. And joint distributions, and we also talked about conditional distributions, if you recall. I mean, if you go back to the previous lecture, we discussed, for example, what this means. This is the density of the random variable y, given that the random variable x is equal to x, and it turns out to be like the joint density divided by the marginal density of x. Now we're going to focus on this conditional density in the univariate, sorry, in the discrete case, it would be like a PMF, conditional PMF, same formula, but for PMF. Because this is like a density, or this is like a PMF, it will have a mean, which would be just basically integral of y against this. So you're rating values that the random variable takes times the probability. This is going to be the probability that is nearly equal to y. And so this is a notion of mean for this conditional density. So that would be denoted like this. So it would be the conditional mean of y given x. Okay, so assuming that x has taken value little x, what is the average value of y? Okay, or the mean value or the expected value. Okay, so this is called conditional expectation. Conditional mean or conditional expectation. And so you're going to go look at the density of y given x, and then we kind of compute the mean of that density. This will be, I mean, in the discrete case, it would be like this, okay? Is this kind of roughly clear? We're going to do some examples, hopefully clear. The key is this is a function of x. So depending on what x is, this joint density, sorry, this conditional density would change. And so the mean is going to be a function of x. It no longer be a function of y, because we are integrating over y. So we're basically averaging over y. So this is like an average value for y, but it's going to be a function of x. So this conditional density, conditional mean is a function really. And if I evaluate it, I can evaluate it at x. This gives me a random variable. This is really the conditional mean of y given x before I see x. So if I don't see x, x is random, I can think of this as really a random variable. So think of this conditional expectation if I replace basically this with capital X. So first I calculated a particular X, and then I replace it with X. This is written like this. And it might not be gonna not be that you might not be comfortable with this, but once you understand what it is, what this is, it makes a lot of sense. This is really the functional form of this but evaluated at the random x. We haven't seen x. So if I don't see x, you can think of the conditional density as really a random variable. Okay, so this is a number. This is a random variable, which is just that functional form evaluated at the random x. So far, so good. And we write it like this. Okay, expectation of y given x is a new random variable, which is going to be a function of x. We'll do examples. I'm very clear. But this is random. This is kind of a number. Because here we just observe that particular x. This is going to be a deterministic number. So far, so good. It's one of the most important ideas in probability and statistics, as we'll see. Um, so let's do an example, maybe it becomes more clear. So recall this setting where we had a pair of random variables that has the density 2 on this triangle. So this is saying in the region where x is less than y, which is this region, on the xy plane, I have uniform mass because the area of this uh, triangle is 1/2. The density has to be 2 for this to integrate to 1. Okay, so it's 2 on this region and 0 otherwise. So if I want to calculate the conditional density, right? So last time, if you go back last time, what we did is we calculate the conditional density of y given x, let's say. And it turned out to be, if I look at the conditional density of y given x little equal to little x, it would be uniform from x little x to 1. So that's the conditional density. Or distribution, which we got by looking at the conditional density. And like figure, like in the figure, it's very clear. So if I look at a particular x, y can take values from x to 1, and on this line, just everything is uniform, kind of. So it has to be uniform. But you can also do go back and we can do it like via this formula. Just use this formula. Be careful about where to divide and stuff, and then you get the result. Okay, so it's going to be uniform. And so if I want to look at the conditional expectation of y given x, it's just the mean of this distribution. Okay, and we know that the mean of the uniform on x to 1 is x plus 1 over 2. Okay, so you can see it's a function of x. This is a linear function of x. If I want to look at this version, which is going to be a random variable, I just replace this little x with capital X. And so that would give me x plus 1 over 2. And you can see this is a random variable. Okay. And we'll see towards the end that this is really the best prediction of y given x. If I want to predict y only based on the knowledge of x, this is going to be my prediction. If you look at like mean squared error. So if you want to minimize the mean squared error of your prediction, that's how you have to predict. So if I give you x and you want to predict what the value of y is, in this case, you can see it depends on the value of x. And this also shows that they're not independent. So if this conditional expectation turned out to not depend on x, if it turned out to be equal to the expectation of y, uh, this doesn't imply independence. But if they were independent, this would happen because in that case, the conditional distribution y given x would not depend on x. So it would be similar to just unconditional distribution of y. So this would happen. The fact that this doesn't happen implies dependence. Okay, so the fact that this conditional expectation depends on x means they're really dependent. And if, in particular, for example, if you know that x is equal to 1, you know for sure that y has to be 1. There's no other place to go here. And so you can see if I place 1 here, the conditional expectation would be 1. It doesn't tell you like the probability is 1, but in that case, the conditional variance would be 0 if you compute. You can compute the conditional variance. There's going to be something like this as well, which would be just the variance of this conditional density. Okay, this conditional density will have a variance. And if you compute the variance, maybe we'll do it later. This turns out to also depend on x. And at this point, if x is equal to 1, it has to be 0 because there's no way to go, nowhere to go. And in that case, y would be exactly equal to that. Uh, do this as an exercise, okay? Anyway, so that's the conditional expectation. And uh, any questions? We'll have a lot to talk about conditional expectation, but any questions? So, okay, so this is m of x. Because this is a random variable, it has a mean of itself, right? It's a mean, it has a mean, and I can take the mean of it and then compute, for example, this. Let's do it, see what happens. So how do I compute the mean of this random variable? It's a new random variable. I can take the expectation. Can you tell me how to compute this? There's this law of unconscious statistician or something like that. How do we compute? Anyone? It's a function of x. Do you remember there's a natural formula here. Integral little m of x times the density of x, okay? Because it's a random variable, it's just a function of x, I can integrate that function against the density of x. Okay, so let's see what the density of x is. The density of x is, we have done it before, so hopefully that's the density of x, uh, and on 0, 1, and 0 elsewhere. So this is going to be, the function is x plus 1 over 2, and then you get 2 times 1 minus x. The x from 0 to 1, and 3x squared minus 1, 0 to 1, right? And then you have to evaluate it. And if you evaluate it, it should turn out to be 2/3, okay? You do it correctly, hopefully correctly. No, did I? Okay, this is not the other way. Then it would work. 1 minus x squared. And then do it, it should be 2/3. Okay, and if you go back and check what the expectation of y was, it was like 2/3 as well. Okay, so the interesting thing is this is not a coincidence. So if I take, this is really expectation of y given x. So we calculated this as a random variable. You can take the expectation of it. And what we showed really here is like the expectation of y given x. This is a random variable. This is m of x. Turns out to be the same as expectation of x. Sorry, expectation of y. Okay, so if you look at this conditional expectation, if you take the expectation again, it would be just the unconditional expectation of y. It's a very important property of conditional expectation. Sometimes in your book, it's called Adam's law. We'll try to prove it more generally with a discrete case. A couple of slides ahead. Okay, any questions about this? Does it make sense? This is as a random variable has a mean, and I can compute the mean. And it ends up being equal to expectation of y. Questions? Okay, we'll see this example again. So this conditional expectation as a random variable has multiple, or as an operator has multiple properties. First, it's an expectation, so it's going to be linear. Like this is general property of expectation. So if I apply expectation, operate the conditional expectation to ay plus bz, I can pull the a and b out, and then um, basically uh, take the expectation inside the sum. Okay, this should be straightforward. The one that we don't prove, but it's like natural, is if I want to compute the expectation of gx times y, I can pull the gx out. Okay. Roughly speaking, if you want to like just a very short proof is think of this as a little proof of this is expectation of gxy conditional on x is equal to x. Okay. If I do this, then let me do it. I'm gonna do it like alpha so that it's like very clear. So if x is equal to little alpha, this is deterministic. Then when I compute the expectation, I know that x is equal to alpha. So this is really g of alpha, if you wanna understand it. Okay, this is equal to that. This should be easy to kind of convince yourself because I'm conditioning. I know that x is equal to exactly alpha, so this has to be this. Now g alpha is constant. I can apply this result. I can pull the constants out. So the constants come out. I get g alpha expectation of y given x is equal to alpha. And so because this holds for any alpha, right? This is saying if I look at this as m of alpha, sorry, this is m of alpha. Let's call this, I don't know, r of alpha. This is saying r of alpha is equal to g alpha times m alpha. I'm going to apply it to this holds for all alpha. I'm going to say, I'm going to replace alpha with x, and this should be g of x times m of x. Okay, so this is really going to be expectation of y given x, and this is expectation of gxy given x. Okay, and so it shows that this is equal to g of x times that. Intuitively, once I condition on this, this is constant, it comes out. Okay, this is a very useful property which is not doesn't have any counterpart in the unconditional case. In particular, if I look at the expectation of g of x conditional on x, it just comes out and I just get 1 here, and the expectation of 1 is 1. So you just get g of x. So you get completely deterministic. Not deterministic, but you don't have to do anything. It just comes out directly. Okay, so these properties are very useful. Um, allows us to compute conditional expectations in cases where we don't need to really worry about densities and such. Okay, let's say proof of 2. Like a heuristic proof. Any questions about this? Properties of conditional expectation. Let's use a like a prop like a little example here. Like it's useful later. So if you look at y, and I mentioned that this is really a prediction, as we'll see, like a prediction of y. And so this is really prediction error. So if I predict y using m of x, the conditional mean of y given x, this is the residual in a sense. This is the difference between my prediction and y is going to be a random variable. This will turn out to have conditional mean 0. Okay, so if you look at the expectation of r given x, right, this is the expectation of y minus mx given x, right? Using the linearity, I can move the expectation inside. I get this expression, expectation of y given x minus, actually, let me do it one more step. So you get expectation of y given x minus the expectation of mx given x. This is by linearity. So this is exactly as the one here. This comes out because of this property. Okay, because m of x is a function of x, it comes out, you get that. But notice that this is really m of x by definition, so this turns out to be 0. Okay, so the conditional mean of r given x is 0. And if you think of conditional expectation as prediction, this is saying if I want to predict the residual given x, the best prediction is 0. There's nothing left. So it's like kind of consistent. If I could still predict it, I would add that prediction to m of x. This is saying once you predict it, this is basically like the essence of the proof that we'll see later. Because of this property, this shows that there's nothing left to predict in the residual based on x. So after using everything x tells us, the remaining error has no systematic direction at any value x. So there's no way to predict this using x. So this follows from the properties. I'll talk about prediction hopefully shortly. But this is the basic idea, and it follows from the two properties that we mentioned. Any question? Comments? So this residual has conditional mean 0. Okay, we'll see by Adam's law I also have, if I apply expectation on both sides. We'll see, like if you apply expectation, another expectation on both sides, this would be the unconditional expectation, this would be 0. So that holds for unconditional expectation. So this is the Adam's law. Let's try to prove this. So it's like the law of total probability, but for expectation. So called law of total expectation, Adam's law, or sometimes called Tower property of conditional expectation. Some people call it smoothing property. Generally, taking expectation is some sort of a smoothing operation because it's an integral. Integration is like smooth things out. Property, smoothing property, or law of total expectation. It has many names. Adam, you can see like there are 4 names at least. So what it says is that if I take an expectation of a conditional expectation, it gives me the expectation of the original random variable. So in order to prove it, again, look at this. This is like a function of x. So if I want to compute the expectation, it's similar to what we did. So this is like that function. Let's say this is m of x, lol x. And I'm going to multiply it by p x of x and sum over x. So here we're assuming things are discrete, but you could do it with integrals as well. I'm doing it with the discrete because I want to interchange the summations or the integrations. In the discrete case, there's no condition. In the continuous case, you have to worry a little bit about whether you can interchange the integrals. But anyway, so this is the definition of. So this is, if you look at it from the definition, this is the definition of m of x. Okay, so I'm integrating or summing this times the y. So this gives me the conditional mean of y given x, because I'm multiplying the values of y times the probabilities that the random way it takes those values under this conditional law, conditional distribution. So that's m of x. And because I'm computing the expectation of this, I'm basically summing the values that it takes times that. So this is really law of unconscious statistician. And I forgot how what was the probably law of the unconscious lotus, the unconscious statisticians, plus the definition, okay, of conditional expectation. At this point, we switch the summation. So I switch x and y. So I get summation y and then summation x, and we get y, pyx, y given x, and then I move this as well inside. Now I can pull this out. This comes out because it doesn't depend on x. We're summing over x, right? So this comes out here, and this product, it would be just p xy joint density. If you look at the definition of this, if you basically plug that definition, it's the joint divided by the marginal, and once you multiply by the marginal of x, you get the joint. Okay, so what I end up having is summation over y, summation p x y xy over x, but this is the marginalization. If you remember, if you sum or integrate one of the arguments of a joint distribution, it gives you the marginal, the marginal of the other random variable. In this case, we're summing over x, so it gives me the marginal PMF of y, and so this is really this quantity. Again, this is really the definition of the expectation of y, the way we define it. Okay, so this is really a simple proof that this expression always holds, or like this law is always true, and this is true for the discrete. So for the continuous case, basically anytime that this expectation exists, I mean, we didn't talk about really expectations existing, but these integrals have to be finite. And in the case of integration, as long as this quantity is integrable, uh, then this will be true. Questions about this argument? You just have to realize that this is a new random variable of it's a function of x. I can use the law of the unconscious statistician to calculate its expectation, and then you just plug in, rearrange the, like basically change the order of the two sums, and then use the definition of conditional density or conditional probability mass function to get the result. So this is by marginalization, kind of marginalization idea. Okay, so multiple kind of concepts that we discussed are at play. The law of unconscious statisticians, the definitional conditional density or probability mass function, and the marginalization idea. This is called the Adams law, law of total expectation, Tower property, smoothing property, depending on who you ask. Everyone has a name for it. So it's a very important property. So what, like intuitively what it's saying is this. So if you think of the expectation as averaging, this is saying if I partition a population by x, so think of x as a grouping variable, okay, especially if it's a categorical variable, like it could be groups. So let's say, yeah, we'll see an example shortly. Like x could take two values, let's say two groups. So this is saying expectation of y under x being group 1 and then under x being group 2, I separately calculated. Those are conditional expectations. So these are averages within each group. Okay. So average y within each group, and then average those group means. This is the outside expectation. This is saying this is going to be the same as the overall mean. So if you group a population into two groups or three groups, and then you average the values within each group, and then average the group averages properly. You have to properly average based on the mass. This is the same as if you average over the entire population from the start. So this just accounts for correct averaging. So one population can have more mass than the other. Okay. Any questions about this or this interpretation? We'll see like an example of this. It's really good to think about this as like groups. It helps understand what is going on much better. Maybe let me give you an example because that will become very clear. So imagine the x here, let's call it s because that would be like the state of the world. Let's say I have s determining the traffic level. Okay, so you either have low traffic or high traffic, and s is the state of traffic. So either light or heavy. So this is just mnemonic, could be 0, 1, or something like that. So it takes two values. It's a binary value. So it takes value L, let's say probably 0.75. Most of the time it's light, and heavy 25% of the time. Okay, so that's the marginal probability of L, like S. It's like marginal probability or distribution of X, if you want. Probability slash distribution, depending on how you interpret it, of S. And then given S, the two states, I'm gonna look at another variable, which is like the time it takes, for example, for me to go from A to B, or someone like a general person to go from A to B. Okay, this is the travel time between 2 points, Y. And conditional on S being in L, it's like normally it's distributed between 20 and variance 42. And under the heavy traffic, it's distributed like this normal. Normal would mean 40 and variance 8 squared. Okay, both the mean and the variance are large. So is this notation clear, the way that I define it? So this defines the full distribution of the pair. So if I look at the full distribution, this will not have a continuous or discrete interpretation. It's just one piece is discrete, the other is continuous. This does not have a like a density or PMF. It's one of the cases where neither continuous or discrete. Nevertheless, there is a valid joint distribution which tells me how to define, like for example, how to compute the probability that Y belongs to a set A and S belongs to a set B. Okay, so for any subset of uh, light and so this here, B takes all the possible subsets of this, and this takes all the possible, roughly, subsets of R. I should be able to determine this probability, and this conditioning definition, and these two, fact 1 and 2, allow me to do that. Allow me to specify any such probability easily by using the law of total probability. Okay, so I can write this as um, I mean, I'll let you do it, but it completely specifies the joint distribution without necessarily needing to specify like a joint density or PMF. So basically this gives you conditional. So there's a conditional density here. So we do have a, because this is a continuous variable, there's a conditional density. So I can talk about the conditional density of Y given S being, for example, heavy, like, or light. Okay, so given that S is light, this is going to give me a normal, just typical normal distribution. And this is going to give me a typical normal density, which then I can use the total law of total probability. For example, when I calculate the probability that Y is in A, I can write it as the probability that Y is in A conditional on S being light times the probability of S being light plus probability of Y in A given S is heavy times the probability that S is heavy. So I know these values, and these are going to be integral. So this is going to be an integral over A of Fy, Y given L, this is Y given S, dy, and so on, similarly. Okay, so this is the law of total probability in this case. And so I can compute the marginal density. There's going to be a marginal density. So Y will have a density. And it turns out to be a mixture density. So here I'm plotting things. So this is the conditional density of Y given X. Sorry, given S being light, you can see it's like centered at 20. The variance is 4. The other one is the conditional density of, um, what is it? The conditional density of Y given S being heavy. So it's like centered at 40. Variance is 8. 8 squared, so standard deviation is 8. So it's like flatter. You can see like the variance is higher. It's like more flat. And if you look at this distribution, this will have a density. You can compute the density would be basically, because this would be, let's say, PL, this is P high, this would be Fy given Sy given H, right? So if you combine this over A as well, so you get integral A Fy S, let me call this F1 of Y. This is F1 of Y for simplicity. This is F2 or FL. FH of Y for simplicity. So you get FL of Y times pi L plus FH of Y times pi H dy. Okay, so that's the end result once you do the law of total probability. And you can see I'm computing an integral of something over A. So this something has to be the density of Y. And you can see the density of Y is really a mixture. It's a linear combination. So these are the weights. This is like 0.75. Here's going to be 0.7, sorry. This is going to be 0.75. This is going to be 0.25. So the density of Y really is going to be 0.75. The conditional density under light of Y plus 0.25. F high of Y. Okay, so this is going to be FL of Y. This is the conditional density under L. This is the density of this. And this is FH of Y. And so what you get is a mixture. This is called a mixture density. If you plot it, you can see it's just going to be something like that. And it's just this, it just has two peaks. Okay. One peak at 40 and then it's they're merged in a way. You get a single this black thing is the density of y. And so these allow you to create like complex distribution. So it's like multimodal distributions. Okay, so that's a particular setting, and you can see the definition is conditional, and you can do anything you want. So you can compute the marginal, it's a mixture of two normals. These are called mixture distributions. So you can compute the marginal distribution of y and answer any question about the joint behavior of y and s without necessarily writing down a joint density or a joint PMF, which doesn't quite exist in like an elementary sense. So far, so good. So what I wanted to do is, any question about this? I want to like give you interpretation of the expectation, like this Adam's law here. Any question about this? So the way to think about the Adam's law is we have two groups, in this case, two states, and then I have two different means. So under light traffic, I have mean 20. So this is the average of this distribution, like mean of this distribution, like average of this group. And then I have another group, which is under heavy. These are the values. These are the possible values. Basically, I can take any values, but I take it with different weights. And so the mean under the second estate would be this, 40. Okay. And if I look at if I want to compute the mean of y, which would be the mean of this mixture distribution, I can integrate this mixture distribution directly. If you do it, basically you can see like you get 0.75 times the integral of y times this plus 25% times the integral of y times that. So you get 0.75 times the mean of this group plus 25% times the mean of the other group. And this is exactly that Adam's law. Okay, so what happens is that I'm going to basically add these two with different weights. So you get, let's do it here. So what you get is, if I want to calculate the expectation of y, I'm going to write it as the expectation of y given s. So this is a binary variable. This you have to understand. This is a binary variable. Or rather, do it here. Expectation of y given s is a binary variable. It's a function of s, so it's going to take value, s is going to take value L, or so this is going to be either s is L, in which case it's going to take the expectation of y given s would be 20, or s is going to be h, in this case it's going to be 40. So it's really a random variable that takes value 20 and 40, and it takes the value 20 with probability, which is the probability of this. Okay, so that will be the probability of s taking value light, which will be 0.75. Then I multiply that by 20. And then the probability that we take this value is the probability of this will be 25 times that. So this is calculating the expectation of this random variable. Okay, so this is a random variable that takes values 20 and 40 with these two probabilities. And you can see that this ends up being the same as if I integrate, multiply both sides by y and integrate. So it gives you basically the same answer. So you get 25%, which is, sorry, 25 minutes, which is the expectation of the marginal distribution. Okay, that would be the expectation of y. This is rather direct, so you don't need to compute the marginal distribution of y in this case. You can see it's much easier. I could have done this calculation, then you could have written down, it would be like a mixture of two normal random, like the densities, and then try to integrate it. That would be complicated, but this is easy, and intuitively it's just you average under this state and you average under this state, and then you take a weighted average of the values based on the masses. Okay, this will contain 75% of the mass. This contains 40%, sorry, 25% of the mass. And then that gives you the result. Okay, and the reason why this is like goes down here is like I have to multiply this by 25%, this by 75, and then add them up. So that's why this peak is lower than what you see here. Here, you're just plotting the conditional distributions or densities. Here, we have to reweight them when we add them to get the marginal. Okay, that's this kind of law of total probability. So these are the weights that you have to multiply. Okay. I think this is a very good example if you understand it. Any questions about any of this? So this tells you how you construct mixture distributions and how you can use this Adams law or tower property to compute the expectations by conditioning on the state and the interpretation, which is like these are group means, and then you take another mean of the groups weighted properly to get the global mean. Questions, comments? We pause here a little bit. Any question about the mixture model? These mixture models are very common in statistics. And you can see, if I wanted to use a Bayesian network, this is kind of S just implies Y. This is the simple case. It's saying S is determined first, and then given S, Y is determined. So you do the arrow like this. So this is saying Y given S is determined, and then the marginal of S. That's kind of the way that this distribution factorizes. Okay? Bayesian network diagram of this model. Questions, comments? The marginal density is a mixture. It's not a single normal density. That's important to understand. But its mean is obtained without integrating the mixture. So you don't have to integrate the mixture. You don't have to figure out what the mixture distribution is. It's really simple in this case. Simple calculation. Okay, questions? So now that we understand this Adams law, there is another law which is called the Eve's law. So this is a random variable. We computed its expectation. It also has a variance. Okay, the question is, what about the variance? Or rather the variance, can I have a similar decomposition for the variance of Y? Can I break it into within group versus like across group variance? And this is really another generally useful idea in statistics. So we can break the variance of Y by conditioning, and the formula would be a little bit more complicated. So in order to understand that, let's try to, this is called the Eve's law. So basically decomposition of the variance, if you want another way of saying it, is just ANOVA, or analysis of variance, or decomposition of the variance. This also has many names. Or if you want analysis of variance in more practical case. So it's like a probabilistic version of analysis of variance. So what we do is, like, again, we have m of x, which is the expectation of y given x. Let mu be the expectation of y. I have a conditional variance of y given x, which is the condition, which is just the variance of the conditional distribution. So you have the conditional density, let's say, it has a variance. So another way of defining it is just, if you remember what the variance is variance of a random variable is, you look at the variable, you take the expectation, right? You square it. So this is the deviation around the expectation squared, and you take another expectation outside. Okay, if I want to define the conditional variance, I put conditioning everywhere that I am using a distribution. I'm going to put a conditioning here and a conditioning here. Right, so if you look at all the expectations in this definition, let me do it properly. Squared like this. So if I work with conditional distribution rather than usual distribution, I put conditioning on x everywhere I see an expectation. So that would be the definition of conditional variance. So it's just the variance with respect to the conditional distribution. The way that we define this is going to be m of x here, right? So what we have here is this. So conditional variance of y given x would be y minus its expectation conditionally, which is m of x squared, and then I take another expectation, but it has to be conditional on x. every expectation would be under this conditioning. Okay. So this is basically saying how much variation is that. You remember this is the residual of prediction. Okay, so the residual of prediction has mean zero, but it has a variance, and it tells you the conditional variance tells you um, how much variation is left that's not unexplained by x, basically. Okay, given x, this tells you how much variation on average is in the residual of that prediction. Um, the remaining variation after x is known. So if I have this, then I can we'll use this. You see, this is going to appear in the formula. So just maybe need to put this out of the way here. That's the definition. So in order to get the formula for the decomposition of the variance, let's write the y minus mu. That's the thing that we need to square take the expectation to get the variance. Okay, mu is the unconditional mean. I'm going to add and subtract the conditional expectation here. Okay, so we get these two terms, and you can see this is saying the deviation from y from the grand mean or the unconditional mean is written as the deviation of y from the conditional mean plus the deviation of the conditional mean from the mu. So think of this as within group. So this is saying within group x, how far kind of, actually for now it's not within group, but like when you like at this point it's just a random variable. But once we take the expectation, it would be within group. So let's have this decomposition. And then what I want to do is or okay, let's say this is the deviation of y from the mean of the group. That's what we can say. Okay, so the deviation of y from the mean uh, of the group determined by x. So it's like a within group variation. And this is the deviation of the group mean from the grand mean. So this is like the between group variation. Um, okay, so if you square both sides, let's say if I square this, I get the square of that plus the square. So if I want to compute the expectation of y minus mu, I'm going to get the expectation of this squared plus the expectation of this squared plus twice the expectation of the product. So let's look at the expectation of the product. If you look at the expectation of the product, you'd see that I can write this as, let's do it here. So this is a random variable, right? I can write, I want to compute the expectation, and I'm going to do the Tower property or the law of total expectation. This is going to be equal to the expectation of the same thing, this thing, right? And then expectation, sorry. I have to condition on something and a condition on x. Otherwise, like vacuous, and then like that. Okay, so this is some random variable z, let's say. If we call this z, this is going to be z. This whole thing is z. Okay, so this is saying I'm computing the expectation of z, and the expectation of z is really the expectation of z conditional on x. Okay, that's the Adam's law. Okay, now if I plug in, I get the expectation outside, and then the expectation, I have y minus m of x times m of x minus mu conditional on x, right? And then this thing is a function of x because mu is constant and m of x is constant. So this comes out. This I can pull out here. What I get is the expectation of m of x minus mu times whatever is left is this part, which I'm going to leave under the expectation, under the conditional. So y minus m of x. Conditional on x, rather this like this. Okay, and if you go back to a couple of slides before, this is really the conditional expectation of the residual. This was R for us, given x, and we showed that this is 0. Okay, so there's nothing left in y to predict based on x after I subtract the best prediction. This we'll see. I mean, this we proved, but we'll see the prediction meaning. Okay, so this is 0, so 0 times this would be 0, so the whole thing would be 0. Okay, so this cross term would be 0. So what I end up having is when I compute this, uh, the cross term vanishes. So let's do it here maybe rather quickly. Um, so what happens is when I do the expectation of y minus mu squared, it would be, let's change this to that. Okay, what I'm going to get is expectation of the first term, which is y minus m of x squared plus expectation of m of x minus mu squared plus the cross term, which is twice the expectation of this, which is 0. Okay, so this thing is, I can write it as uh, um, expectation of y minus m of x conditional on, sorry. Let's say this is something that I'm calculating. Let me properly do it. Square it, right? I'm computing the expectation of the square of this. So y minus m of x. In order to not write it, let's call this the residual. Okay, this is the residual. So what I'm going to get is that the expectation of the residual squared. Too many. Let's do this. The expectation of residual squared. Okay, and I'm going to do this power property again. Expectation of, or Adam's law, r squared given x. Okay, this is the same as the expectation. I do the conditioning and do another expectation, the same thing. And here, this is just expectation of m of x. We know that, again, this is expectation of y by definition. And it turns out to be equal to the expectation of um, m of x. So I get this mu is the same as this. And then I have a squared. The expectation is applied to both sides. Okay, so let's do the properly. So why this is equal to this, again, this is an example of, so this is by definition E of y, and you can see this is expectation of y given x. So this is another application of the Adam's law. Okay, the fact that expectation of m of x is equal to mu is another application of Adam's law. Okay, so we do it multiple times. So this by definition is, anyone knows what this is? What is this definition of? Anyone? So I have a random variable, I subtract the mean, I square it, and I take the expectation. What is this quantity? Anyone? Sorry. Any guess? This? Yes, so this is going to be the variance of m of x. M of x is a random variable. We're looking at m of x minus its expectation and a square and taking another shade. This is really the variance of that conditional mean. So this quantity, this, if you look at it, this is just a definition. So this residual, they call this R, right? So this is really this quantity, if you look at it. This is R, by definition, the way I defined it. So what I'm having here is the expectation of R squared conditional x. This is really conditional variance of y given x. If you go back, I didn't want to write this down, but you're squaring this and then take the expectation conditional on x, that's the definition of conditional variance. So what I ended up proving is that this side is really the variance of y by definition. So we have the variance of y has two terms, expectation of the variance of y given x plus the variance of m of x is really expectation, remember, y given x. So it has this very interesting symmetric behavior. So it has two terms. It's a little more complicated. So this is called the Eve's law, or the decomposition of the variance. So this is saying in order to compute the variance of y, if I want to condition on x, I have to calculate both the conditional variance and the conditional expectation. This conditional expectation has some variance that would contribute parts of the variance, total variance. And this variance also has a mean that would contribute another. This is like both random. So this is random quantity, this is random quantity. You take the variance now, this is no longer random. You take the expectation, no longer random. So you have these decompositions, okay? So this is really group means. This is the variance of group means. So this is group means. So really between group variation. Okay, it tells you like how variable the group means are, how different they are. And this is the variance within group. This is like saying take the average within group variance. Okay, variance within. Okay, that's the kind of the interpretation. So let's see. Yeah, so what we get is a total variation, which is that is the average of within group variation. This is within group variation, plus the variation of the group means, or between group variation, if you want. Okay, expectation of the variance of y given x plus the variance of expectation of y given x. And the key was this kind of the fact that this cross term vanishes and then a lot of applications of the Adams law. Okay, so basically you write the back and forth between expectation and so we use it once here, the Adams law, and once here again. So go through the proof. In the interest of time, I'm gonna not repeat it, but the proof is not really difficult. You just redo the decomposition, use the properties that we discussed. We know a lot of properties now of the conditional expectation to be able to simplify and then arrive at this very nice formula for you can call it the law of total variance as opposed to the law of total expectation. Okay, so let's go back to any questions about maybe the form? So the conditional variance and conditional mean should be like understandable. They're just properties of the conditional distribution. It has a mean and it has a variance. Anything that a distribution has, it has. But they turn out to be random now because they depend on x, which is random. And so the randomness, that random variable, those random variables have means and variances, and they appear in this law of total variance. Questions? So let's do the example again. So we had the traffic example. We had two states. The probability of each state is this. The conditional means are 20 and 40, and then the conditional variances are given. It's like 4 to the 2, if you remember, 8 to the 2. So these are the information that we gave in that hierarchical model. And then we want to find uh, the variance of y. Okay. Maybe can anyone help me write it down? So I have the variance of y. I want to compute these two terms basically, right? So the expectation uh, we have, right? So I need to calculate the expectation, sorry, the variance of the expectation and the expectation of the variance. Uh, Maybe help me compute the expectation of the variance. This one first. This would be easier. What is the expectation of the variance of y given x? Sorry, given s. So it's a random variable. both of these are random variables. You can see they're random variables that take different values under different states or with different probabilities, right? So this takes values 16, should be easy, 64, with probabilities 0.75 and 0.25. Okay, so that should be the expectation. It's just that the binary variable takes these two values with those probabilities. So that shouldn't be difficult. So how do I compute the variance of expectation of y given s? Anyone can help me do that? How do we do this? There are different ways of doing it. It's just a particular variance. So this is a random variable, takes multiple values, right? So I can, for example, do expectation of, let's call this m of s if you want. M of s squared minus the expectation of m of s squared. Okay. The expectation of m of s, anyone remembers what this is? Adam's law. I'll give you, this is just expectation of y. So this we already calculated. So I just need to calculate this. Okay, and this is really, again, it takes two values. This random variable takes only two values. It's either 20, so you get 20 to the 2. The other one is 40 to the 2, and you get the probabilities are 75 plus 25. Okay, so that would be the value of this quantity. And then minus the expectation of y was 25 from before. Okay, so you should be able to calculate this. So there's nothing very deep here. It's just that these are random variables that take different values. So this is an application of the, again, law of unconscious statistician, this whole thing, like ms squared, let's call it g of s. So you're calculating g of s. So it would be like g little s as s in L and H times the probability that S takes value S. Right? So that's kind of the idea. Law of the unconscious statistician appears a lot. Okay? Because we are out of time, I'm doing it rather quickly, but that's kind of this. So that's the first one. The second one you do, this is doing it differently. So you can also do it from the other expression, right? So like the expectation of m of s minus the expectation of m of s squared. Sorry, the variance. Yeah, that's the variance of this is m of s, right? So we know that the expectation of m of s is 25. This is the expectation of y. So you get 20 minus 25, and then 40 minus 25, and then you square it. This should be a square. And then with these probabilities. Okay, just another way of calculating the variance. And then you compute and you add, hopefully the addition is correct, you get 133. So do that as an exercise. It's a very good exercise to understand what each one means. And in this case, most of the marginal variance, so this is sometimes called marginal variance, because it's just the variance of the marginal of the joint. Joint is like y and s together, and it's like if you marginalize out s, you get y. So marginal variation comes from unobserved traffic state, not from the variation within the fixed state. Y, you can see like this is the 75. 75 is the variation due to unknown state, not the variation within a state. The fact that states vary kind of, it's an interesting, like you can see the decomposition, which one is contributing more, which of the two. In this case, this term is larger. So this is saying that the unknown, that the fact that I don't know S The variability in S is more severe in this case. Not from the variation in the fixed state, right? So the total variation would be like higher, and you can see like this distribution is more spread out. Uh, this distribution is more spread out than either one of them. So the mixture is more spread out. So it has to be bigger, I mean, than in these individual ones. Okay, there's a lot of interpretation you can kind of make out of this, which in the interest of time I'm skipping, but that you get the rough idea. These two terms have meanings, right? One is how far within each, like sometimes you can call it a strata of data. So we are stratifying the data, and then within each strata or group, you have variation that would be this part. And then between the groups, you have this variance, which is due to unknownness of the group. The fact that you don't know the group of Y. If you knew which group Y would belong to, then you just compute the variance of Y given that group. But the fact that you don't know just adds this extra term, which in this case turns out to be really large. Okay, I'm gonna skip this. You do this, do it as an exercise. You can use the same idea, Adam of Eve, like Eve together to compute the expectation of a summation over IID random variables where the number is also random. So I have a sequence of IID, remember, like independent identically distributed. I sum x1 up to xn, but n itself is a random variable, and it's independent of the sequence. And I want to compute the expectation of this sum. And the variance has two sources of variation, one the x's and the other the endpoint, the stopping point. And so you condition on n, and it will be fixed. You get like n times the mu. And the variance would be n times the variances because they're IID, conditional on n. And then you can use if you take another expectation out of this, just you get the expectation of n. So you get mu times the expectation of n. If you do the eves, you get a more complicated statement which like combines the expectation of this and the variance. So it's a very good exercise on how to deal with or how to use these. In this case, because n is random, it makes things complicated. We condition on it. Once you condition on it, it's like fixed. You can treat it as like if I fix it equal to n, it would be just n times mu, and then just replace it with capital N. So the trick is always to do conditional on n being a little n. If it's complicated for you, then everywhere just capital N becomes a little n, and then it's easy to calculate. And then once you're done, you replace back with capital N, you get like a random quantity. Um, if, for example, n is Poisson, the mean and the variance would be kind of the same. So you get something like this, which is interesting. Just read about it this line. Okay. Question? I mean, that's any of this so far? We have about 15 minutes actually to talk about the prediction idea, which is really the punchline. Um, Questions about Adams and Eves and conditional expectation and variance? Um, so this example will be a little bit tough to discuss, but what it's saying is we'll come back to this maybe after we discuss the rest. So suppose you have a uniform random variable that takes values in -2 and 2. And then conditional on x, or not conditional, but let's say y is x squared plus noise. Okay, noise is independent of x squared. So conditional on x, expectation of epsilon is 0. If you plot the scatter plot, you can see like the scatter plot of the points are these blue points. Okay, and if I give you x, um, roughly the best prediction would be the midpoint here. So the midpoint of the spreads would be that, and I mean, that's the best I can do potentially if I want to minimize the average error. If I predict it by this point here, I'm gonna predict things that are, let's say, let's fix this. I'm gonna maybe fix this line, right? I'm gonna assume that x is this. So I know that points are in this range, basically, maybe, like roughly, mostly. If I predict by this value, the things that are close to this are predictable, but things that are here are like predicted very bad. So you can imagine that it's best to predict by the center point, which is really going to be the mean. Okay, and so if I'm here, I'm going to predict by this point. If I'm here, I'm going to predict by this point. Here, I'm going to predict by this point. It turns out that basically the best predictor would be just the expectation of y. Um, expectation of y. Sorry, yeah, expectation of y given x would be the best predictor, which in this case would be the expectation of x squared plus epsilon given x. You get expectation of x squared given x plus expectation of epsilon given x. This is 0 by assumption, and this comes out, you get x squared. So the best predictor is really this line, which is natural, okay? If you wanted to predict based on a single value, the best single value would have been just the expectation of y. This you can also prove. And the expectation of y in this case would be potentially, you can compute it, would be 4 over 3. And this is going to be this line. You can see it's not going to be a very good approximation. It would be good if things were linear, but you can see there's really a nonlinearity here. And then if you predict based on x, it would be much better. And we can show it. So the best linear predictor here is losing a lot compared to the best predictor. I want to like capture this idea of best prediction. So what do we mean by best prediction? So in this case, for example, the constant function is not the best predictor. The quadratic function is the best predictor. In order to formalize this, what we can say is, suppose I want to predict y by a function of x, and I want to look at the difference, the squared of the difference. If it turns out that this is constant, then the constant function would be the best. So I want to minimize over all possible g. I want to find a function whose residual after, so this is going to be prediction of y based on x, my prediction. If you give me x, g would be a deterministic function. I can form a prediction. For example, would be x squared. I can say I'm going to predict y to be x squared. And then this is the error that I pay on average. Okay, so this is called the mean squared error of prediction. This is the mean, this is the squared error, so the residual prediction. So the idea is that when I try to minimize the function that comes out is going to be the conditional expectation. In other words, we're going to prove that the expectation of y minus m of x, that conditional mean, is going to be less than or equal to the expectation of y minus g of x for any g, for any function g. So among all functions g, the one that has the smallest prediction error in the sense of MSE is going to be the conditional expectation. In particular, if I use the constant function, you can actually show, oh, let me talk about this later. But this is the meaning of conditional, like conditional expectation being the best predictor. Okay, so why it's the best predictor? Why is this inequality true? So look at the residual. That's the residual, and I'm going to write this side y minus g of x as r, which is going to be y minus m of x plus m of x minus g of x. Okay, so I can write the residual of that prediction. This is going to be a residual of prediction based on m of x plus m of x minus g of x. So this is really we are adding and subtracting m of x. You can see you get the y minus g of x. Okay. Now, if I square both sides, you can look at the expectation of y minus g of x squared. I get three terms. I get expectation of r squared plus expectation of twice, basically. Twice, this is using linearity expectation. Expectation of r times m of x minus g of x. Yes. Okay, let's call this delta x if you want for simplicity. So you get r, this is r times delta x plus expectation of delta x squared. Okay, so this is just a function of x. And the fact that this is a function of x, right, causes it to come out of the expectation. Sorry. Okay, let's do this. I want to calculate this cross term. So you have the expectation of r times delta x. We're going to use the trick that we had. So we do the Adams law or Tower property. You get the expectation of r times delta x. And I'm going to condition on, I'm going to condition on x. And then another one here, okay? So in this inner conditioning, delta x comes out because delta x is a function of x only, so you get the expectation of r given x, and then another expectation outside. And you can see, I mean, we have seen this before, that expectation of the residual of this particular residual, this a couple of slides before, we've proved that this is 0. So this whole thing has to be 0. Okay, so this cross term goes away. And now you see what happens. So this is the prediction error of g of x. This is the prediction error of this guy, right? This is the prediction error of based on conditional expectation plus something which is non-negative. This is always going to be non-negative because this expectation of something is squared. Okay, so we prove this identity. The expectation of y minus g squared is equal to the expectation. This is the r squared, expectation of r squared. This is the prediction error of the conditional expectation, and this term is always non-negative, okay? Because this is always non-negative, this side, this has to be always greater than or equal to this, which shows this inequality. So this is always greater than or equal to this by this much. And you can see it's only going to be 0 if this is actually equal to that. Because this is always going to be 0 if m of x is equal to g of x almost surely. Okay, so this proves that the best predictor in the MSE sense is the conditional expectation, because every other estimator would have this extra term if it's not equal to m of x, and that's not negative. Okay, so this cannot be removed. So the first term cannot be removed using x. The second term is the extra error from using g instead of m. If you set like g equal to m, this goes away. This you can optimize over. And so like this part is, there's no way to fix it because we can't change m of x. That's part of the distribution. Okay, so thus m of x minimizes the mean squared error or prediction error, the mean squared of prediction error among all functions of x. That's why it's the best predictor. It minimizes the mean squared error. If you do the same argument, but instead of g of x, you say you're looking at the constant, then you can do the same thing by saying, okay, expectation of y minus the general constant squared is equal to the expectation of y minus expectation of y here now. Let's call this mu. The cross term, again, you can argue it vanishes. You get the expectation of, actually, you'd get mu minus, there's no expectation, mu minus a squared. So the same argument shows if mu is expectation of a. Y is the best constant approximation or prediction would be mu, because this side is going to be non-negative, and if a is equal to mu, this is going to be equal to this side. So as any other a would be bigger than or equal, like causes your prediction to be having an extra term. So the best constant predictor would be the expectation of y. This one you can prove as an exercise. It's like a simpler version of this. And the best functional prediction based on x would be just the conditional expectation. So in this example, this line is the best constant prediction. If you want to predict it by a constant, this is the best. If you want to predict it based on any function of x, this is going to be the best one. Okay, it beats the constant one by a large margin. So this has a much smaller prediction error. You can see things that are here are very badly represented by the constant predictor, but by the best predictor based on x, it's like that. This example is very interesting because the covariance of x and y is 0. Okay, they're not correlated. The way to show it, if you look at the covariance of x and y, you would get covariance of x and x squared plus epsilon. You would get covariance of x and x squared plus covariance of x and epsilon by, let's say, by if they're independent, this is going to be 0. And this one would be, let's say, expectation of x to the third minus the expectation of x times the expectation of x squared. So if x is symmetric, like has a symmetric distribution, both of these would be 0. So if x is symmetric in this case, which is uniform, then they're going to have they're going to be uncorrelated. So that a priori seems to be they're uncorrelated. But if I give you x, there's a lot of information. Okay, so conditional behavior is different than unconditionally. So they're uncorrelated. It may seem they're not, but they're not independent. If they were independent, then this would end up being equal to the E of y, which would be the best constant predictor. But they're not independent. So although the covariance is 0, there's a dependence, which is once you condition, you can see it. It turns out to be x squared, and this is really the best predictor here. Okay, questions about this? Yeah, if you force yourself to be linear, we could also find the best linear predictor. Maybe I'll talk about this later. So the best linear predictor would be something else. So this is the best constant predictor, the best linear predictor. Actually, the best linear predictor, I think in this case would be actually the constant predictor. Yeah, so in this case, the best linear predictor and the best constant predictor are the same, and they're different than the best predictor given x. I'll come back maybe talk about the best linear predictor. You can use the same ideas to find the best linear predictor, and it would be basically the population level regression function, like linear regression function. This is the general regression. This is sometimes called the regression function. This is the regression function of y given x, non-parametrically if you don't make any assumptions. If you force yourself to be the best predictor among linear functions, then you'd get the best linear regression function, which we'll drive later, maybe, and then I need to talk a little bit about the covariant Gaussian, but these two slides remain for the next lecture. Any questions, comments? So this example, I'll encourage you to go through. I will come back later. But this idea that the conditional expectation is the best predictor among all functions of x in terms of the mean squared error is a very fundamental property. And we already proved it. The proof is like basically because of this fact that we showed earlier, which follows from the property as a conditional expectation. Questions, comments? Okay then, thank you, and we'll see you on Wednesday.